Now we've got a constant substrate concentration S, an initial microbial biomass concentration of X naught, and we're asked to derive an expression for the microbial biomass concentration as a function of time, X of t, using the Monod equation. All right, so step 1, Monod equation, dx dt is going to be equal to mu x, and mu is exactly equal to mu max, which I'm just going to denote with a subscript m just to keep things a little bit cleaner. And that's going to be multiplied the ratio of s over ks plus s, and this is all still times x. Okay, so now same step as normal. We're just going to get all of our x's on one side, meaning I'm going to divide both sides by x to bring this over here, and I'm going to multiply through by dt to get the t over here. So what we find for step 2 is that we have 1 over x dx is equal to mu max times s over ks plus s dt. Okay, and the important thing to know here, this is a constant that depends on the microbe, so this is a biologically relevant constant. We are told that the substrate concentration is constant, so S is constant, and again, Ks is also a constant. So that means this whole term is constant, so this is exactly like having our variable K times dt from our previous video. So we're going to integrate this. Both sides, 1 over x dx equals the integral of mu max times s over ks plus s dt. Our integration bounds, we're still going from time equals 0 to some arbitrary time t, and we're still going from x naught to some value x of t. Okay, and then what we find, I'm going to continue right here. The integral of 1 over x dx is just going to be natural log of x. Technically, it's the natural log of the absolute value, but since we're dealing with a concentration of biomass, we're never going to have a negative value, so we can just write that as natural log of x of t minus natural log of x naught is going to be equal to this constant times t. So mu m s over ks plus s, and all of that is times t. Okay, so now in order to solve this for x of t, we have to remember how natural logs work. So natural log of a minus natural log of b is exactly equal to the natural log of a divided by b. Okay, so we're going to use this expression to reduce this from 2 natural logs to 1. Let me make some room. Okay. So we're going to have natural log of x of t divided by x naught is exactly equal to mu m times s over ks plus s, quantity times t. And then now what we're going to do is we're going to use a second natural log trick. So we already used natural log of a minus natural log of b equals natural log of a over b. Now what we're going to use is the fact that e to the natural log of x is exactly equal to x. Okay, because remember, we're trying to get x of t equals yada, yada, yada. So what we need to do is get this x of t outside of this natural log. And we know that we can do that by taking e to both sides of the equation. So if we do something to one side, we have to do it to the other. So that gives us x of t over x naught is going to be equal to e raised to this entire power. So mu m s over ks plus s, and we've got a t up there. All right, I'm going to make some more room up here. Okay, and the last thing we need to do to get x of t by itself is just multiply both sides by x naught. So we're going to have, continuing, x of t is equal to x naught times e to mu m s over ks plus s quantity times t. All right, and then that's our final function. So what we see from this example is if we start with something that looks like dx by dt equals some constant times x, we know that the solution is going to look like x of t equals x naught times e to the kt. Okay? So before, when we just had a constant on one side, we ended up with a linear function for x of t. Now when we have a constant times x on the right-hand side, we get an exponential function.